Hi everyone. Hey, today we get to talk about chemical reactions. And let's start with acid-base reactions. Okay, molecules that donate or give away an H plus ion are called acids. And those molecules that accept them and bond to those H plus ions are called bases. And hydroxide ion is a very common base. Now, you might be asking yourself, how come there's a whole field of chemistry devoted to the H plus ions? Okay, there's a lot of other positive ions out there. Sodium's probably the most common one. Sodium starts with 11 electrons, 11 protons, and when it loses one, this one, if it's gone, then you have the sodium cation. Lithium, same thing. Kick this one out, it has 2 electrons, still looks like an atom, but hydrogen, when it loses its one and only electron to become H+, it's simply a naked proton. That's not a complete atom, so it's special. It's an incomplete atom, and it's highly reactive. And so we have a whole field of chemistry devoted to the free proton, the H+ ion. Oh, and since it's such an important field of chemistry, oftentimes chemists will write the chemical formulas of the acids listing the hydrogen first. So a very common acid found in stomach fluids is hydrochloric acid, and the H is listed first. Here's an example of an acid-base reaction. We'll take that stomach acid, HCl, and react with water, and the hydrochloric acid is going to be the acid. We need to donate H+. So take away this H and give it to the other molecule. And the H has to come off without any electrons. It's positive. And so after it leaves, chlorine's left behind bearing a negative charge because it keeps all the electrons. The hydrogen comes off as a naked proton. And then that naked proton bounces over here on the water. So instead of 2 H's, it now has 3. And the hydrogen came over with a positive charge. So now the whole thing is positive. Water here accepted the H+ ion, so now it's the base. Let's look at a different acid-base reaction. Let's start with NH3. That happens to be ammonia. NH3 is a base, so it's going to accept H+ ions. That forces water now to serve as the acid. And so it has to give away an H+ to ammonia. So ammonia starts with 3 H's, and with 3 H's, and then it gets an extra one. So now it's NH4. And it's also positive because H+ is positive. If we look at the structure of water, and if water had to give away the H but kept all the electrons, well then, now we have an oxygen atom with 3 lone pairs and 1 hydrogen. And it turns out this oxygen's negative. It kept all the electrons. And H+ left. And so something positive leaves. That means the fragment left behind is now negative. And that's hydroxide ion. Oh, and you may have noticed that here, water can sometimes act as a base and sometimes as an acid. Oh yeah, the H is listed first. So there you go. Sometimes it's an acid. There's another very common acid-base reaction, the old Volcano reaction seen in some science projects, right? This foamy stuff coming out of the volcano. Actually, they mix in some soap to make it extra foamy. But the main reaction involves pouring in some vinegar. That's what this little flask has, some vinegar. And this white solid is baking soda. And the chemical formula for baking soda is NaHCO3, also known as sodium bicarbonate. The molecule found in vinegar that gives it its tartness, its tang, its sourness is acetic acid, and the H is listed first. Yep, it's an acid. So it's going to give the H+ over here to this molecule. Well, when that happens, the H+ leaves, the remaining fragment here is going to be negative. And if we go to the periodic table and we look at what happens to metals like sodium bonding to nonmetals like the Hc and the O, those are all nonmetals, the bond is ionic, and sodium is positive. And so when another positive ion comes over, that H+, they trade places. So now bicarbonate is the actual base. It's going to accept H+, So instead of 1H, it's going to have 2. It's going to form H2CO3. And it turns out that molecule falls apart. It's not stable. They have 2 H's, take 1 oxygen and make water, and leaves behind a C with 2 O's. That's carbon dioxide. And then we form a new ionic bond between the sodium and the fragment left behind from the vinegar. And the key to the volcano reaction is the creation of CO2. That's a gas, and that's what's causing all the bubbles, all the fizzing. Okay, let's break it down a little bit more. The key ingredient in the volcano reaction is the baking soda having bicarbonate. With the bicarbonate ion right here, it reacts with the H plus from the vinegar, so the base, bicarbonate, is going to accept the acid, H plus, and get an extra H, and there it is, H2CO3, carbonic acid, that's unstable, and it falls apart to form water and carbon dioxide. We got these double arrows here because this is a kind of reaction that is reversible. It means that sometimes this molecule goes this way to form water and carbon dioxide, but there's other times when the carbon dioxide and the water react with each other and go back to carbonic acid. But being unstable, it can follow this downward arrow here and return to H plus and bicarbonate. And then, moments later, these two can combine once more and go back and forth. And the reaction is said to be in equilibrium, where they're constantly bouncing back and forth, left to right, right to left. Okay, up above in the volcano reaction, bicarbonate accepts H plus. That makes it a base. But there's other times when that H listed first can act like an acid. So the H can donate, the bicarbonate ion can donate it to hydroxide ion, and then it loses an H to become CO3 2 minus. The H plus went over here with hydroxide ion, and now the oxygen will have 2 H's. The minus and the plus charges will cancel, and it'll form water. Okay, but the bicarbonate ion acts as either an acid or a base, depending on what's reacting with it. In this case, H plus, an acid, or hydroxide, a base. That actually has biological consequences. In fact, our blood is buffered by the bicarbonate ion, and it prevents changes to the pH in blood. Where does all this bicarbonate come from? Well, so the gases that we're exhaling contains carbon dioxide. Well, some of that stays behind in our bloodstream, reacts with water, and makes its way to bicarbonate ion. Okay, I just mentioned that bicarbonate ions try and maintain the pH, prevent it from changing. What is pH? Well, it's a way of measuring acid and base strength. It's a way of measuring acid or alkaline solutions. And so if you have equal numbers of hydroxide ion, a base, and hydrogen ions, the acid, equal numbers, then we say it's neutral. And it turns out in pure water, nothing else in there, it turns out the water will break down reversibly to form hydrogen ions and hydroxide ions. And the number of H pluses in solution is 1 times 10 to the minus 7 moles per liter. Remember moles, Avogadro's number? Yeah. So in a liter of water, there'll be 1 times 10 to the minus 7 moles of H plus ions in the water. And there's an equal number, right? This is a balanced equation. So every time you get one of these, you also get one of these from one water molecule. So there's also 1 times 10 to the minus 7 moles per liter, and the M here stands for moles per liter, and they're equal. And so that's when you have a neutral solution, when they're balanced. And then, if you gain more H plus ions by adding something else to the water, well then you're going to make more of those H pluses, and they're going to go up in value from 10 to the minus 7 just to 10 to the minus 4. And then the hydroxide ions go down. And with more H pluses, now you have a more acidic solution. Now what's the pH here? Well, pH means power of H, or the exponent. So right here, if you have 1 times 10 to the minus 4, well, we're just looking at the 4. The pH is 4. And properly speaking, if you don't have a 1 in front, you really have to take the logarithm of the number of H plus ions in solution. And then notice that the concentration, the number of H plus ions, is negative. So we drop the negative sign when we report the pH. They're positive values. And so the trend is the lower the pH, the lower the value. A 2, for example, is even more acidic. And here's some common solutions. Stomach acid, I mentioned, contains hydrochloric acid, a very strong acid, so the pH is between 1 and 2. Lemon juice, quite tart, it's very acidic, it's above 2 but below 3. Cola, well, cola is carbonated. It has CO2 in it, which reacts with water to form carbonic acid, which then falls apart and forms some H plus ions and the bicarbonate ion. Okay, so all this carbonated soda makes the solution acidic. Cool. And then there's vinegar and beer, black coffee and stuff. Okay, so now the pH is actually getting closer to neutral, and that's where blood is. Pretty close to neutrality. Slightly alkaline. So alkaline means the pH is above 7. It's somewhat basic, not acidic. We got seawater. And then there's ammonia. We mentioned that's a base. And so the pH is around 12, meaning we have a lot of hydroxide ions and less H plus ions. Okay, let's look at a different type of reaction. Now let's look at oxidation-reduction reactions. Sometimes they're abbreviated. If we look at the ox and the red from reduction and swap them, we call these reactions redox for short. Redox reactions. But what's really going on is that one molecule is releasing electrons and the other one is picking them up. So sometimes we call these electron transfer reaction. In these reactions, we say one compound is going to lose electrons, and that compound is said to be oxidized. Where'd that name come from? Well, oftentimes during an oxidation-reduction reaction, the compound that ends up losing electrons will then gain oxygen atoms. And with more oxygens, we would say it's been oxygenated or oxidized. Has more oxygen atoms, but not every time. If a compound's losing electrons, they have to go somewhere. They go to a different compound that picks them up, gains them, and then we say that that compound is reduced. Where did the origin of that name come from? Well, the first oxidation-reduction reactions are metals that contain a lot of oxygen, and in the reaction you get rid of the oxygens, the oxygen atoms, and so now the materials weigh less, so they're reduced in mass. And so it turns out this reaction right here, a very hazardous and toxic reaction to create table salt, is an oxidation-reduction reaction. The balance equation says take 2 atoms of sodium metal, that's this material right here, take 1 molecule of chlorine gas for every 2 atoms of sodium. Okay, chlorine gas is this gas right here. And then mix them together. You get a little reaction, lots of light and heat. And then you go in there and scrape out the material, which is table salt. So how is this an oxidation-reduction reaction? I don't see any oxygen atoms. Well, yeah, this is an example where there's no oxygens. Well, let's see if we can find some charges. How about these pure sodium atoms? Nope. The charge would have been listed in the top right of the compound. So these are not charged, they're neutral. What about Cl2? 2 nonmetals attached together are covalently bound. Okay, so there's no charges here. The chlorine atoms are attached through a covalent bond. How about in the compound NaCl? Well, chlorine's a nonmetal, but sodium's on the left side of the table. It's a metal. And when we pair up metals with nonmetals, the bonds are ionic. So somebody's positive and somebody's negatively charged. Yep, these atoms are trying to get to the same number of electrons that the noble gases have. So chlorine is trying to go from 17 electrons to 18. So it needs 1 more. And if it can get 1 more, it'll be Cl minus. Sodium starts with 11 electrons. Wants to have 10 like neon. So it's trying to kick out an electron and become positive. So what happened? Sodium was neutral, and then they became +1 cations. How did they become positive? They lost an electron. They lost 1 electron each, and that means they were oxidized. Where did that electron go? Well, each atom of chlorine in this molecule is neutral, no charge, but afterwards they have charge. They are negatively charged. Where did that negative charge come? It came from that extra electron. So Cl2 was reduced. Those two atoms gained electrons. 1 electron each. So here's 2 ways of trying to remember that. So oilrig, that stands for oxidation is loss of electrons. Reduction is gain of electrons. Or you can say Leo the lion says grr. And Leo is loss of electrons is oxidation. Gain of electrons is reduction. Here's another example of a redox reaction. We have iron ore, also known as rust, Fe2O3, being mixed with carbon. And carbon exists in many forms. This form is probably charcoal or graphite, and probably not diamond. And in the reaction, you get iron metal and carbon dioxide, a gas. So how is this an oxidation reduction reaction? Let's look at charges. Find iron on the periodic table, and there's no valence number here. And if you try and say, hey, iron starts with 26 electrons and either wants 18 or 36, well, that's too many electrons to gain or lose. So it turns out the metals here in this gap, called the transition metals, they do something different. They can vary the number of electrons they want to lose. Right, most metals lose electrons. And so in order to predict their charges, look at the other element. Look at the oxygen. What's the charge on the oxygen if it makes an ionic bond? Well, it starts with 8 electrons. It wants 10 like neon. So it wants to pick up 2 electrons. The oxygens are going to be -2. And there's 3 of them in this molecule for a total of -6. We got 2 iron atoms that somehow have to balance this -6 charge. Right? Nature wants to create neutral compounds. If it didn't have a neutral charge, the charge would be listed in the top right of the formula. No charge listed, so these are neutral. So to balance the charge, the iron atoms have to be +3. So that together they add up to +6, and they balance the charge. Okay, so the iron started out as +3, and then now there's no charge. How'd that happen? Well, to cancel out these positive charges, it gained 3 electrons. So this one's being reduced. The iron ore is being reduced, and that means the other compound must be oxidized. Now, there's no charge on this carbon, and afterwards the carbon's involved with another nonmetal. 2 nonmetals make a covalent bond. So there's still no charges. Darn it. It's hard to track the gain or loss of electrons. So then we're just going to use that little trick that if it gains oxygen, it's probably being oxidized. Here's another oxidation reduction reaction. We have magnesium metal, this metal strip here, stuck in the hydrochloric acid, and it's fizzing away. Okay, what's going on here? Well, hydrochloric acid, H listed first, this molecule is donating H+ ions. And then the chloride is becoming negatively charged. Afterwards, we have the same 2 elements, hydrogen, hydrogen, connected together. That's a covalent bond, no charge. But magnesium chloride, MgCl, what's that? Well, magnesium's on the left. That's a metal. Chlorine's on the right. Non-metal. We have an ionic bond. And so magnesium, being the metal, wants to lose electrons. It wants to lose 2. Either the 2 valence electrons, or it starts with 12, wants to go down to 10, and wants to lose 2. become a +2 cation. And chlorine wants to pick up 1, become a -1 anion. Okay, so looks like the chlorine atoms are not changing their charge. They're just spectator ions. They're not doing anything. Instead, H+ is becoming neutral. And Mg, which was neutral, is becoming positive. So in order to become positive, it's going to have to lose 2 electrons here. So the magnesium is being oxidized. The hydrogen ions are gaining electrons to neutralize the positive charge here. They're being reduced. Okay, last oxidation reduction reaction, the Bunsen burner. CH4 is natural gas, methane. It's mixing and burning with oxygen in the air to form carbon dioxide and water. And, most materials that have carbon in them, when they burn, they form carbon dioxide and water. All I see here are a bunch of nonmetals. So everybody is involved in a covalent bond. Great. Without ionic bonds, we can't track the charges, we can't track the electrons being transferred. So we're going to have to use the other idea that whoever's being oxidized is going to gain oxygen. And so if you focus on the carbon before, no O's connected the carbon. Afterwards, 2 O's, the carbon atom gained oxygen. So we're going to say that methane, CH4, is oxidized. That means the O2 molecule must be reduced. Last topic, organic chemistry, a whole nother field of chemistry. This one is devoted to carbon. You may have heard the expression that we're carbon-based life forms. Yeah, so the molecules of life often contain carbon. You can break this down, look at it more closely. Look inside the nucleus, you got the chromosomes, break those down, look really closely, and you can see the DNA. And look really closely to the DNA, and we see the building blocks of DNA contain something called nucleotides. And if you stare at this a little while, you see that they're leaving out some C's here. Right here there's a C, there's a C there, a carbon atom, and one right there. And it turns out carbon bonds 4 times. So we're missing some H's too. And that's a common thing to do. That because these molecules of life contain so many carbon atoms, and carbon bonds 4 times, they oftentimes bond to hydrogen. Well, when they start drawing these big molecules, to simplify the drawings, we start leaving out the C's and the H's. So we're going to have to get used to those types of drawings. There are other drawings where the C's are completely left out. And those are called stick drawings or skeletal structures. And they're drawings of molecules in which the letter C has been omitted. The letter H has been omitted, but only when it's attached to carbon. If it's attached to another element, we keep the H in there. And then you look at all the entire molecule, and any bonds of hydrogen, you take them out. So here's a 3-dimensional shape of the molecule. And what we're going to do is change this into a skeletal drawing. So what we need to do, well, first take out the C's. Next, take out the H's when they're attached to C. But this H is not attached to carbon. It's attached to oxygen, so I have to leave it in there. Finally, all the bonds of hydrogen are taken out. And that's all that's left. Let's clean it up a little and just connect these lines together and then bring this H in closer, and we get the skeletal drawing for ethanol. Let's count up how many carbons are in phenylephrine. Well, every place you see a bond that doesn't have an element listed is carbon. So there's a carbon here. That's 1. Carbon, 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 carbon. We've got 6. Carbon right there at that intersection of the lines. 7. Carbon here. 8. Ooh, there's a C listed. 9. And there's one more here. 10. We could look at the formula that there's 10 of them. How many hydrogens are there? Well, this carbon has 1, 2, 3 lines coming out. Carbon bonds 4 times. Remember we had that little trick that the number of electrons an atom wants to gain or lose equals the number of bonds it usually makes. So carbon's in column 4A. It wants to either gain 4 electrons to have 8, or it wants to lose 4 electrons, start with 6 and go down to 2 like helium. Well, lose 4 or gain 4, it wants 4 bonds. That's what it usually gets. Back to this carbon here, we only see 3 lines coming out. Carbon bonds 4 times. So there's a missing hydrogen up here. This carbon, 2 lines come out, 1 line goes down. Yep, it's missing a hydrogen. Ooh, but this carbon has a bond here, a bond there, and 2 down, it's got all 4. Same is true for this carbon, there's 4 bonds. This carbon has 4 bonds. This carbon we only see 1 bond, but there's 3 attached hydrogens, a total of 4 bonds. Same is true for this carbon. Okay, we've drawn in all the hydrogens, and it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 3 is 12, and 3 more is 15. Good. Got them all. Okay, finally, let's just be aware that nature likes to put carbon into hexagons. And she also likes to alternate double with single bonds. This molecule is called benzene. That it's a flat molecule, and if you flip it over, you can alternate the double bonds in this way or in this way. And they're the same molecule. Or you could rotate this, right? Just spin it a little bit so this one spins to look like that one. And so it doesn't matter if you put the double bond up here or over there and then alternate, it's still the same molecule. So an even faster way of drawing the skeletal drawing is just put a circle in there. And what we're going to have to know is that this drawing means benzene. It means this. Okay, thanks for watching.